Well, hello and welcome you to Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here in my virtual classroom. One thing different in my virtual classroom today is I'm not going to have anything on the screen. I'm during peak electricity hours, so as a teacher, I got to cut corners on costs anyway I can, and that's the way I'm going to do it. Today what we're going to be learning is solving systems of equations like last time, only this time, instead of doing it by graphing, although I think the first problem has some graphing on it, I'm going to be solving using a method called substitution. There are three popular methods. We did the graphing, substitution here, and elimination will be my next video, or at least that's the plan. And solving by substitution, thankfully, is stuff that you've probably done all of the processes before. So now we got to put it all together as one and say, how does that make an effective strategy for solving systems of equations? Two different equations with x's and y's in them, and getting the answers for x and y. And what that means on a graph. I think that's how number one's answered. So to get into this, I do have 15 practice problems for you to do, for me to do with you. And of course, as that can take up time, one way for me to save time here is not really teaching what's happening so much. I mean, I'll say it as I'm doing it, but I'm really just going to talk about effective strategy. And I think that the more problems that you see me do, the more you make sense of, all right, so that's how you do it. All right, so I think if I just go ahead and get started now, I think that'd be our best go-to. Let's go ahead and start with number one, which, like I said, does have a graph for it, but not yet. In the system of linear equations shown here, the value of y is given. This will be the only problem, I think, where a value is actually just given. Use this value of y to find the value of x and the solution of the system. So we have two equations. Doesn't matter that this doesn't have an x in it. This is an equation for the system. And these two systems, or these two equations in the system, both work together. So in the system, we happen to notice that y equals 12. Y doesn't just equal 12 in this equation. Y also equals 12 in this equation. 12 is an equivalent value for y, so I'm going to substitute 12 for y into the other equation, and then I'm going to solve for x. So right here, substituting 12 for y, I have 2x minus 12 equals 4. And I'm using parentheses for emphasis that it is a substitution. It is 2x minus 12 equals 4. I'm going to go ahead and add 12 to both sides there, and I will then get 2x equals 16, divide both sides by 2, and I get x equals 8. So x equals 8 and y already equaled 12, and those are my two values that work together as one, but the solution is an ordered pair. The solution is an ordered pair, and we do 8, 12 as if to say if we did graph these, which we will, if we did graph these two, this is the point of intersection of those two particular lines. See, x doesn't just equal 8. X only equals 8 when y equals 12, and that's the only solution set that's actually valid for the system. So let's go ahead and graph this system of linear equations and see how the solution of B compares with A. Ideally, they should be the same. So if I didn't do anything wrong, we should be set. I'm going to start with y equals 12. Y equals 12 is a horizontal line. Let me put it in like this lighter blue. Y equals 12 is a horizontal line at literally 12 for y that goes all the way across forever. 4, 8, 12 right here. Y equals 12 looks like a line like this. That's the blue line. It's like y equals 0x plus 12, 0 being the slope. 2x minus y equals 4. I'll do this in green right here. I'm going to do the intercepts method since it's in standard form here. If y equals 0, then 2x equals 4, which means x equals 2. That's my x-intercept. If x equals 0, negative y equals 4. That means y equals negative 4. That's my y-intercept. So my x-intercept at 2, 0, this is 4 right here. So 2 is going to be halfway in between like that. Okay? And then there's y equals negative 4. Oh, you can't see that on my screen. I'm sorry. It looks like that. And then y equals negative 4 is right here. So it looks like if I draw a line through there, well, let's see where this thing ends up. And obviously I'm going to have to stretch it out some. But right here, and then right here. Let's see if I can get this one. Stretch you. All right, so I'm stretched out there. And it should be crossing, it should be crossing at 812. That doesn't look very pretty in comparison to what I kind of wanted there. So let's see if there's something I can do to address that. X equals 2, y equals negative 4. I guess if I really, there we go. These aren't really closely to scale just yet. I guess it's supposed to look more like this right here. I'm doing this as a confirmation of this is what the answer is supposed to be. and I want to show it with a decent looking graph. I'm really trying to fix my points. So I guess if it looks more like that, then look, it crosses right there. So I guess my point of 2, 0 wasn't perfect. That's on them, honestly. That's on them for not giving me a better scaled graph with the actual mark of 2. But I'm going to take that. That point of intersection right there is indeed, well, let's get that blue, darker blue, is indeed 8, 12. And that's how they compare. They are the same. The solutions are the same. So that's number 1. That's a first example of it. Notice that my 12 did substitute in the other equation, though, for y. I have to do that each time. Okay, number 2, 3, 4, and all of these from here on out, except for the last two, 14 and 15, they're solving systems. You're going to see 3 problems per page, and we'll just move on. They'll get more difficult or different special cases, like no solution and stuff. We'll see what those look like. Solve each system of linear equations by substitution. So in terms of substitution, you saw in the last problem that y actually happened to equal a certain number, and I could substitute that number in the other equation to solve for x. I'm going to do the same thing. I'm going to substitute something for probably y. I can choose one of these 2 equations, like this bottom equation. If I take this equation and if I rewrite it so that so that the 2x moves over here and y is by itself, I will now have y equals negative 2x plus 5. It's like in slope-intercept form almost, so just imagine you're rewriting like that. Now I have an expression written in terms of y right here that I can use and substitute in my other equation. Now why am I actually doing this? I guess I said I wouldn't be teaching it, but I can as I'm talking about it. Why am I doing this? Well, let's look at what happens when I substitute this. I get 5x plus the quantity negative 2x plus 5 equals 8. What I've done was I've taken one of my equations that had both x and y in it, which was unsolvable on its own. I can't solve for x or for y when the other is actually there, not as a number. But I took one of my equations, I expressed it only in terms of x when I applied that substitution, and now I have one equation with one variable that has an x in it right here, and I can actually solve for x. I've expressed y in terms of x from one of my equations and used it in my other equation. So that's what I'm going to do here. Adding a negative 2 becomes minus 2, or 2x, and adding a 5 becomes plus 5. So the parentheses were rendered useless, but I'm still going to stick to parentheses for when they actually matter. Combine like terms, 3x plus 5 equals 8. Hopefully you're okay with me just saying subtract 5 from both sides. Subtract 5 from both sides, I get 3x equals 3. Divide both sides by 3, you get x equals 1. And like the previous problems, I am not yet done. I have to still find y, and I still have to write my answer as an ordered pair. So let's go ahead and go back, and I can substitute 1 for x into any equation that of my choosing. Any equation that I'd like. You have to remember that in the system of equations, x would happen to equal 1 for both or either for this thing to work. Just like the last problem, x doesn't just equal 8 in one equation, x equals 8 for the whole system. I guess there only is one x in this equation. But the point is that x equaled 8 in both equations here. You can see that here. X is 8 on both lines. So here, I can substitute 8 for x in either equation right here. Or because I took this equation and rewrote it and turned it into here, I'm going to substitute 8 right here. Or 1, excuse me, it's a 1. I'm going to substitute 1 into x in this equation. I think it's the fastest way to solve for y. Y is already isolated in this equation. It would be very wise of me to go ahead and go this way. So negative 2 times 1 is 2, negative 2 plus 5 is 3, so you get y equals 3. So we end up getting the system solution of 1, 3. Now I'm not going to double check these problems. You saw in the past problem how I did the graphing video, how I went ahead and did that. But to double check, substitute 1 in for x and 3 in for y in both equations and make sure that it works for both. It's not enough for it to work for one. It has to work for both. Okay? That's what makes a system solution valid. Okay, that was one way that I did that problem where I isolated a variable. Notice I got y by itself in the top equation in order to play the substitution game. So here I'm going to get another variable by itself, and I think if you recognize the way that I got the other variable by itself in the first one, I chose one that was already just y. I didn't choose like 5x where I'd have to divide by 5 to get x by itself. So smartly here, this time I'm not going to get y by itself. Y is being multiplied by a negative 3 and a positive 5. I'd rather get x by itself in this problem. And actually with this problem too, like if I take the top equation, I add 3y to both sides. I'm going to get x equals 3y plus 10. I'm going to go ahead and for this problem, even though I could substitute 3y plus 10 into this equation, and if you want to do that, go ahead. Let me show you a different approach. It's something called the equal values method. It's a method of substitution where I'm going to rewrite this equation and solve for x as well by subtracting 5y from both sides, and I'll get x equals negative 5y minus 22. Now, I'll be honest, this isn't necessarily faster. I'm just giving you the approach that you could do this as well. If the goal is that the x is going to be the same, we assume we can get an x. If the goal is the x is going to be the same thing for both, then if x equals this and if x equals that, remember the same x, then these two expressions must equal each other. So by substitution, in essence, I'm going to take this 3y plus 10, which x equals, and replace it with, say, that x right there. Basically, I'm going to set this expression equal to this expression. So I can make it say 3y plus 10 equals negative 5y minus 22, like that. Okay, now I can solve for y here because I have one equation with one variable, and that's the end goal. So I'm going to add 5y to both sides, so I get 3y plus 10 plus 5y equals negative 22. And I think right here is where you can see why the steps that I took to make that happen didn't necessarily make this problem go faster. What would have I done if I just took, let me erase this for a second so it's kind of out of the way. What would I have done if I just took this equation right here and substituted it in to this variable for x right here? What would I have? Well, I would have this. 3y plus 10, which is x, plus 5y equals negative 22. So I'm kind of back to where I was anyway, but I'm just giving you the idea, if you have a variable isolated in both equations already in your system, just set them equal to each other. If x equals this and x equals that, then this equals that. It's a cool thing called the equal values method. You can look it up more. I likely won't do that more on these unless there are already variables isolated, but I'll be honest, I think all the rest of the problems are in standard form until you get to the word problems. So maybe when we get to the word problems, I'll go ahead and do that. All right, let's go ahead and solve for y. Combine like terms here. 3y plus 5y equals 8y. 8y plus 10 equals negative 22. Let's go ahead and subtract 10 from both sides. And negative 22 minus 10 is negative 32. And divide both sides by 8. You get y equals negative 4. As always, we are not finished with our answer. We need an x, and we need an ordered pair. We need an ordered pair, therefore we need an x, therefore. So, I'm going to go scroll down the screen more in a second. I need to find my x. So I'm going to use this equation up here. It's all positives. I like positives more. You like positives more. Let's deal with that. X equals 3y plus 10. Even though I'm going to plug in a negative. X equals 3, y plus 10. Notice, y equals negative 4, and another substitution is occurring. 3 times negative 4 plus 10. That's negative 12 plus 10, which is negative 2. Negative 2. So our final solution for this one is when x is negative 2, y is negative 4. That's negative 2, comma, negative 4. If you want to check these out when you graph them, and you don't have to graph them, but if you want to go to a graphing calculator, find the site. It's called desmos.com, D-E-S-M-O-S. It's a nice plug for them. And you have an online graphing calculator there. And what you can do is you can type in these equations straight up. Use the plus and minus and equal signs, numbers and letters, and type this equation in one thing, and it'll just draw the graph immediately. And type the other one, it'll draw the graph, and then it'll show where they connect. You can click on the dot, and it'll show that these two would connect at negative 2, comma, negative 4. Okay. All right, bye-bye, Desmos. Free plug. This video is brought to you by Desmos.com. Desmos, where all of your answers are just a typing of a graph away. All right, number 4, 5x minus 3y equals 22, negative 4x plus y equals negative 19. Going back to strategy and talking about this one more time, my first step in these things in order to solve by substitution is isolating a variable. Let's get one of the variables in one of the equations by itself. And I have 4 choices. I have the x and y on top, the x and y on bottom. The last 2 problems that I did, the y's were by themselves on number 2, or there's a 1y, and there were 1 x's on number 3, and now on number 4, it doesn't seem that it's exactly that. Let's take a look again. It looks like at number 4, this x is multiplied by 5, this is multiplied by negative 3, this y, this x is negative 4, and this y here looks pretty clean up. I'm guessing, strategically, that the fastest way for me to go ahead and solve for this stuff is to go ahead and get this y by itself. All I have to do is add 4x to both sides right here. And that's the most advised way to go about it. Make no mistake, no matter which one you get by itself, you can get the right answer. I'm choosing the y for the sake of speed. And you know what else? That's a line from SpongeBob. You know what else is that the other ones would give you fractions. And I'm going to talk about that more when it comes to if we have to use something where we divide by something. Strategically, which one would be best and safest to do. Y equals 4x minus 19. I'm going to take 4x minus 19, this expression that is equivalent to y, and I'm going to substitute it in for y in the other equation. Remember, it has to be the other equation. And I say that, you might ask why it is. If I substitute this back into its own equation, you're just going to end up getting something that says 0 equals 0. You've put the equation on top of itself in another form. So nothing, it just says it's an infinite number of solutions for what you have. So there's nothing there to talk about. This equation is different. It's a different line. So it's maybe, it depends. But they're going to intersect at one point. That's what we want to find. 4x minus 19 takes place of y into here. Let's go ahead and do that. 5x minus 3. This is where parentheses are the first time that they actually really matter. 4x minus 19. Remember, that represents y. Equals 22. So again, I just rewrote the top equation, but with y, I have 4x minus 19. This is a case where they throw it into you pretty fast here. Now we got to distribute that negative 3 into 4x and negative 19. And remember, that 3 is negative. It is not a positive 3 here. So we're going to get 5x. Negative 3 times 4x is negative 12x minus 12x. Negative 3 times negative 19 is a positive 57. And that all equals 22. And the rest is, I don't want to say the rest is algebra, because the whole thing's been algebra, but the rest is the basic solve for your variable. I got negative 7x plus 57 equals 22. If I subtract, by the way, I just combined like terms here. If I subtract 57 from both sides here, I get 7x equals, negative 7x is negative 35. And divide both sides by negative 7, I get x equals positive 5. So as you see, I'm going to do less of the writing in between. When you ask how'd you go from one to the other, I'm saying it out loud to you. I divided both sides by negative 7. You know, eventually it is a good practice to actually get that part out of there. I don't want to condone it for those who still have trouble with, you know, mentally taking care of that or ignoring negatives or something. But if you feel you're ready for that next step, it's quicker. It is. All right, 5 is not the only answer. I need to solve for y. Let's use this equation to make it happen. Let's do this mentally right here. Is that okay? 4 times 5 minus 19. All right, that's 20 minus 19, so y equals 1. Y equals 1. So that coordinate pair is 5, 1, and that's my answer. All right, so hopefully you're getting the gist of the substitution thing. Eventually, they do get harder in terms of choosing what to get by itself or forcing you to use fractions. Or maybe the answers are fractions, I don't know. Or no solution or an infinite number of solutions. But that's the gist. Isolate a variable, right? Get a variable by itself, and it's your choice. I'm going to choose the one that's going to be easiest for me. So isolate a variable, substitute that expression into that variable of the other equation, and then solve an equation as you normally would. And then when you get that solution, use it for the other, to solve for the other variable. Okay, if I solve for y, I'm going to use that y and solve for x. Okay, and you notice where I went ahead and I substituted these things in each time. When I found out one of them, like this 5, I'm going to plug in the easy equation, the one where I already isolated y. And this one right here, when I solve for y down here, I put it in the equation where I already isolated x, and I isolated it twice. Heck, I chose this one. X is already by itself. It's going to be a very quick way to go about it. All right, here we go. 5, 6, 7. Same stuff, maybe some more negatives it looks like here. Same kind of problem, so I'm going to jump straight into it. Probably not much to talk about other than this is the one I'm going to get alone. Makes sense? That's a 1x. So subtract 7y from both sides. I'll get x equals negative 7y minus 11. Substituting negative 7y minus 11 in for x in the other equation will give me negative 2 times the quantity negative 7y minus 11 minus 5y, it's a lot of negatives here, equals positive 4. There's a positive. Good news, a lot of this other stuff is about to turn positive now too, about everything. In fact, if I distribute the negative 2 into a negative 7y and a negative 2 into a negative 11, I get positive 14y plus 22. And you say, hey, there's still a minus there. Well, guess what? 14 is bigger than 5. 14 minus 5 is 9. So 14y minus 5y is 9y. 9y plus 22 equals 4. So much for all those negatives. This virtual classroom can withstand all those negatives right there. All right, let's go and solve for y. Oh, here comes a negative. Let's go ahead and solve for y. If I subtract 22 from 4 for both sides, 4 minus 22 is negative 18. So I'll get 9y equals negative 18. Divide by 9 and get y equals negative 2. Okay. And once again, I'm going to substitute the negative 2 into the easiest way that I think I know I can. You can choose whatever equation. I don't care. But I'm going to plug it into the one where I have x by itself already. I'm trying to solve for x. Why not? So x equals negative 7 times negative 2 minus 11. The negatives are back, but not for long. X equals 14 minus 11, which is 3. X equals 3, and my final solution for number 5 is 3, comma, negative 2. And that, as they say, is that. Nice small numbers. Very clean so far. Okay, number 6 is the first kind of problem where we're seeing 4 variables, the x's and the y's in 2 equations, where none of them are a 1, right? I don't have a 1x or a 1y anywhere to be seen. So now the question is, do I still isolate a variable? And if so, is there a better choice compared to others? The answer, I forget what the first question was. Do I still get a variable by itself? Yes. Is there a better choice than others? Most of the time. Is there in this case? Yes. Now, let me show you all four variables that I can isolate here. I will actually show you the result of isolating all 4 variables. And I want you to tell me which one you thought was best. And furthermore, which way we can come up with it very fast. By isolating a variable, that means getting it by itself. So I can take the top equation, and let's say that we get x by itself. Getting x by itself means that we would subtract 6y over here. So I'd get 2x equals negative 6y plus 16. And I'll just show you the step this one time. I'm going to divide everything by 2. You divide both sides by 2, but that means divide every term by 2. You don't choose on this side. Everything divides by 2. So I get x equals negative 3y plus 8. So I got x by itself right here in the top equation. Okay. Now I'm going to go ahead and take the top equation here, but this time I'm going to get y by itself. And I'll get, by getting y by itself, I have to first subtract 2x over. So I'm going to get 6y equals negative 2x plus 16. And if I divide, I have to now divide both sides by 6 here. Okay. And so that's going to give me y equals negative 2 over 6 reduces to 1/3. So negative 1 over 3 x plus, this reduces to 8/3, 8 over 3. Okay. So that's getting y by itself. How about this? How about I stop right there? And I already ask you, which one do you think is a better solving for isolating and substituting? X or y? All right, time's up. All right, I hope you said x here. With x, I don't have any fractions. With y, I have 2 fractions. And not to hate on fractions. Well, actually, you know what? I'm going to hate on fractions. Fractions suck. No, they're worthwhile. But if I don't have to use them, I'm not going to. All right, so I'm going to avoid using them at all costs if I can help it. And I'm going to do that. So I'm going to choose the x in that case here. Now, what about the bottom equation? You might ask, well, Mr. Robinson, you want to try the bottom equation? You said you would. Let's talk about the thing that I wrote in black here, dividing by 2 and dividing by 6. Notice these were the coefficients of the original terms here. With 2x, I had to divide by 2. With 6y, I had to divide by 6. What did I have to divide by 2 and 6? Every term in that equation. So what you can do before you rewrite anything, because I don't want you to rewrite all 4 and make a choice, is mentally ask yourself, if by solving for x means I have to divide everything by 2, can every term here, the coefficients and the constant, divide by 2 and leave me with integers? The answer to that was yes. If I divide by 2, I have no fractions. I have all integers. How about the 6? If I solve for y, I have to divide everything by 6. Can these divide by 6 cleanly? No, these can't. We just saw that. So let's look at the bottom equation. If I want to get this x by itself, I'm going to divide everything by 3. Can everything divide by 3 cleanly? 2 of them can. The 3, obviously, and the negative 18 can. 5 can't. you'll get 5/3 somewhere. So that's no good. And then same with y. I'd have to divide everything by 5. So if I divide this by 5, obviously, that'd give me y. And then this gives me 3/5, and this gives me 18/5, negative, I guess. But the point is, those are fractions. So the only one that left me with no fractions, the golden ticket for me on this particular problem, was this top x. And this top x, when I got it by itself, let me kind of circle that. When I get this x alone here, it seems to have left me with the best possible choice to do it. So there is a strategy involved when it comes, there is a strategy involved when it comes to which one you want to choose to do and why. Sometimes you're left with only fractions, and then you take the least of all evils. Maybe the one that has the most positive numbers, or the one that has the smallest fractions, or one fraction instead of two, or maybe you're okay with fractions. It all depends. And by the way, if you use fractions, there is a way to get out of it in the end by multiplying both sides by the number it's dividing by, and I might have to run into those and I'll show you. And don't forget that sometimes your answers are also fractions anyway, so sometimes they are just unavoidable. Even when the rest of the work leading into it wasn't a fraction, sometimes the answer also is. To be honest, I don't know if we're going to run into fractions in these practice problems. Let's go ahead and look at this problem now that we have number 6. All right, number 6, I isolated x in which equation? The top one, which means I'm going to substitute negative 3y plus 8 into which x? The bottom one. All right, remember, it has to be the other equation for this to work out. So that's a 3 times x, so that's 3 times, let's divide this. That's 3 times negative 3y plus 8, which is taking place of x, minus 5y equals negative 18. Reminder, I am using this equation right here, and I'm substituting negative 3y plus 8 in for x. Okay. After distributing here, we're going to get negative 9y plus 24 minus 5y equals negative 18. Negative 9y minus 5y is negative 14y. If I can for you, I'm going to do the next step right now. I'm going to subtract 24 from both sides. I'm moving it over to the right side. Excuse me. I have to start isolating y. Negative 18 minus 24 is the opposite of 18 plus 24, so that's negative 42. Ah, not a fraction. Good. And divide both sides by negative 42, we get y equals 3. In solving for x here, because I'm short on room, I'm just going to go ahead and kind of mentally take care of it. Substitute it right in here. Y is 3, so x is negative 3 times 3, which is negative 9, plus 8, which is negative 1. So x equals negative 1 right there. And of course, we write our answer as an ordered pair, which I'll do in blue. I'm going to get negative 1 for x, 3 for y. That is the answer among answers. Okay. So, not a long problem. I spent the beginning talking about the philosophy stuff, and it looks like we have to carry that through. So, hopefully you notice that it's a good strategy to kind of employ so you don't play with it too much or deal with fractions, the fraction headache when you don't have to. So, I'm going to do the same thing here. None of the x's or y's right now have a coefficient of 1 or negative 1, and I'm going to have to divide. If I divide the top equation by 7, no dice, fractions. If I divide the top equation by 2, not a fraction here, but a fraction here. Hopefully we can fare better on the bottom. If I divide everything by 6, fractions, even though they're 1/2, they're fractions. If I divide everything on the bottom by 3, looks like it's good. Looks like this thing will pan out right here. I'm going to isolate this y variable. I'm going to get this one by itself. So let's go ahead. Adding 6x to both sides, I get 3y equals 6x plus 3. Divide everything by 3 without me having to actually write it. This becomes y. This becomes 2x. And this becomes 1. So y equals 2x plus 1. Very clean positive slope-intercept form appearance of an equation. I feel good with that one. I'm going to substitute 2x plus 1 in for y in the top equation. Okay. So we're going to get, remember that's this one, 7x plus 2y, equals 24. Distribute. You can tell the problems start to get a little, we've done them before. So you'll see me sometimes speed up a little more here when I say, I want you to try and do this problem a little. You know, I'm walking through it. I'm making it happen. Combine like terms here. Making it happen, but I'm waiting for the next kind of problem to occur. One that we haven't seen yet, maybe a no solution case, maybe something where we have to use fractions or the answer is fractions. You've now run into these. So if you feel good about these, time to move on, right? So I get x equals 2 by doing all the necessary steps. And again, hopefully we can get a good how did we go from one to the other. I subtracted 2 from both sides. I divided both sides by 11. That's the that's the end goal. Learn the basic algebra in a quick manner. That helps with the rest of it. Y equals 2x plus 1. If x is 2, well, 2 times 2 plus 1 is 5. So I'm going to get y equals 5 as the other guy. So y equals 5, and of course the ordered pair would then be 2, 5. All right, so far all the problems have been very good and solid and working out, and I felt nice about them. Jump on over. This is number 8 coming up next. Yep. Let's go to number 8, 9, 10. Okay. Solve each system linear equations by substitution. Now, from the onset, because I'm already looking at this, that there's something peculiar. From the onset, you're probably looking at it and saying, this problem looks easier than the others. What's wrong with it? And look, there's nothing really wrong with it. But it's a special case. It is different. X plus y equals 3. Is there a better variable to get by itself, y or x? I would argue probably not. Harder, easier. I generally like to get y by itself because I like y equals mx plus b. But even before that, if we want to talk about another strategy here, even though we're not trying to get one of these two by itself because it takes more work, there's nothing wrong with sometimes making your values smaller than they have to be. Or than they, there's nothing wrong with making them smaller than they are. Excuse me. If you notice immediately that all these numbers could divide by 4, why not do it? Equation manipulation. I'm going to do this more when I do the elimination method video next time. But, you can take these equations, you can reduce them or grow them to your whim. If I wanted to, I can divide all of these things by -4 or +4, whichever. How about -4? How about that? Everything by -4, that becomes a 1x and a 1y and a -3. So I rewrote my equation here, just like I would have with any other one with manipulation, and I turned it into x plus y equals -3. Now look at this top equation. We get x plus y equals +3. Very interesting look in these two equations here. They're very similar looking. And what's actually also interesting about this, I'm doing this problem way differently, just for the sake of doing it, is that notice that x plus y is the same expression on both sides of this thing. It is x plus y. So I don't actually even have to isolate a variable by itself. I don't actually have to get a variable by itself if both of these are equal representations. Remember if I said if y equals this and y equals that, then this equals that? Well, if x plus y equals this, and if x plus y equals that, then this equals that too. So an equation that I'm going to write right now is 3 equals -3. And you're sitting there going, what did you just do, Mr. Robinson? You messed up. I didn't. This equation system is a little different. When you get something like this and you trust that you did the math right and x and y become irrelevant points in it because, look, they're gone, you have either a true statement or a false statement. This one happens to be false. 3 doesn't equal -3. So this ends up being one of those cases where you say no solution. You say no solution. And in a no solution case, that means that the lines, in fact, are parallel. These are parallel lines that never cross through each other. And look, you could do the problem any way you want. You want to isolate y for me and plug it in? Go ahead. You're going to get left side doesn't equal right side, and it's going to say no solution. You're going to say no solution regardless, and that's what this was. I wanted to be different for that one, and I was. You want me to be normal again for number 9? Sure, I will. Even though it looks like we're in the special case realm probably here. I'm not going to divide everything by 3 up here. You want to? Go ahead. That's fine. I'm going to go ahead. Let's get this y by itself. It's already positive. And if I add this x over, that will be positive as well. So I'll get y equals x plus 5 on the bottom equation. I have isolated y. I'm going to substitute x plus 5 in for y in the top equation. And we'll get 3x minus 3 times the quantity x plus 5 equals -15. If I distribute the -3, remembering that it is negative, so it will affect the signs of both terms inside there, we'll get 3x minus 3 times x, that's 3x. -3 times 5 is -15. Minus 15 equals -15. Weird. 3x minus 3x is 0. These two are gone. I get negative 15 equals negative 15. You can leave it like that, or you can say, hey, if you add 15 to both sides, you get 0 equals 0. Yeah, it doesn't matter what you do at this point. The left side equals the right side in this particular problem. Something went wrong again? No, nothing went wrong. These two equations are the same. They are identical. You don't see them as the same because they're not in y equals mx plus b form. Well, this one is now. But if I rewrote this in y equals mx plus b form, I'd get y equals x plus 5. They are the same line. When you get a 15 equals 15, a 0 equals 0, that is what is called an infinite number of solutions. Which is basically another way of saying that because these are the same line, there is more than one x and y that I could substitute into this to make it work. Which x and y's can you choose? I don't know. Go ahead and make a table out of this. Take the equation. Here's x, here's y. If you plug in 1 for x, you get 6 for y. If you plug in 2 for x, you get 7 for y. 100 for x, 105 for y. There's an infinite number of solutions. I plug in something for x, I get something for y. Remember, they're the same line, so they're intersecting everywhere that they go. So there's not one answer to it. It's just an infinite number, and we're good. It's called a dependent system. Number 10 here, I'm going to go ahead and get this x by itself in the same process. And like I said, if you know that these can divide by 3, and you feel like you want to do something with that, go ahead. I'm just going to go back to normal form. Add 8y to both sides. I get x equals 8y plus 17. I said I wouldn't teach this stuff, and look, telling a teacher not to teach is like telling well, I shouldn't say telling water not to be wet because people argue water's not wet. It's like telling the Kardashian. I'm not going to go that route. Okay, 8y plus 17. So negative 3 times the quantity 8y plus 17 plus 24y equals negative 51. Distribute. See, this is why you might want to see if you can divide something, because now my numbers are just going to get obnoxiously big. I'm fine with it, but you might not be. Negative 3 times 8y is negative 24y. Negative 3 times 17 is negative 51. So negative 24y minus 51 plus 24y equals negative 51. Negative 24y plus 24y make them go bye-bye. And you get negative 51 equals negative 51. Just like last time, we have the left side equaling the right side. Where there are no x's and y's, they have become irrelevant in the case. Because whatever you plug into them, that's a solution in one equation is a solution in the other equation. Once again, this is a dependent system where we have an infinite number of solutions. I might as well copy and paste that right over here. Infinite number of solutions one more time. And that's, well, maybe more than one more time. I don't know what problems come after this one, but there you go. This is the special case row. This is the special case page right here where you have all those. And I was glad to have run into some of those. Okay, 3 more problems before we hit the word problems. And I really am hoping to dive into some fractions. Not like I'm giddy for them, because you will run into them someday and you might want to know what to do. Okay, so here we go. 5x minus y equals 18. 10x minus 2y equals 32. Just kind of once again with those things, just to make you aware, even though I'm probably going to get this y by itself, keep in mind that all these could divide by 2. So if you ever want to play with smaller numbers, divide this whole equation by 2. Make it 5x minus y equals 16. Positive 16. I don't know why I wrote a negative. You would just write it like that, and then boom, now you got another one you can play with here. All right, but I'm not going to do that because you might not know what to do with that. Maybe you saw it and you said, no, it's not for me. Let's go and get this y by itself here. I have 5x minus y equals 18. I'm going to subtract 5x from both sides. And I'm going to get negative y equals negative 5x plus 18. You might notice that I always write the variable term first here. I'm used to writing things in what's called standard form. And furthermore, not standard form like this. I mean standard form of a polynomial. It's a different take. X's come before constants. The other thing is that, it's like slope-intercept form. So if you ever wonder why I do that, Mr. Robinson, why don't you write 18 minus 5x? That looks better. There's nothing wrong with it. Just, sometimes people develop habits, and that's what they do. This is negative y equals. I probably would prefer positive y equals because I want to plug it in right there. So divide everything by negative 1, multiply everything by negative 1, switch the signs. If I switch this sign into positive y, this becomes a positive 5x. This becomes a negative 18. Y equals 5x minus 18. There, now that doesn't look so bad, because now this is positive. 5x minus 18 substitutes in for y into this equation. Now, you might have seen what I wrote as the equation when I divided by 2 before, and you might have already run into a thought of what this answer is going to be. I'll give you a hint. I don't think we've lost ourselves from the special cases problems just yet. Negative 2 distributing gets negative 10x, and a positive 36 right here equals 32. 10x minus 10x, see ya, thank you for coming, and we get 36 equals 32. Not a true statement. Whoops, not in my lifetime. 36 does not equal 32, something wrong with that, and we are going to go ahead and say no solution. Once you've eliminated x and y, and the left side does not equal the right side, it is a no solution case. That does mean the lines are parallel. They do not intersect. Okay, it's one of those cases where there is no x or no y by itself here. Now, interestingly enough, because again, I see things that are coming into form with this problem. Interestingly enough, no matter what variable I want to get by itself, it'll lead to a fraction. If I divide everything on the top by 2, a fraction right there. If I divide everything on the top by 3, a fraction right there. If I divide everything on the bottom by 4, a fraction here. And if I divide everything on the bottom by 6, I get a fraction there. So no matter what, there's going to be a fraction in my answer when I isolate a variable. But if you can, if you can look big picture in this problem, and you can see the whole problem, but if you can look big picture in this problem and say, gee, I can divide all these by 2. It doesn't get a variable by itself, but if everything here divides by 2, look at what you get. Just for a second, let me indulge you with this. We get negative 2x, negative 3y, and positive 12. Well, look at the top equation right here. Negative 2x, negative 3y, and positive 12. Gasp. They're the same equation there. And, you know, some people still might have kind of a concern with it, saying, but Mr. Robinson, they're not the same equation. You divided everything by 2. They weren't the same before. You'd be right in saying, like, yes, this equation is twice as large as this one, but as y compares to x, they represent the same values, okay? As y compares to x, the same values still apply. It is the same equation. It is manipulated from the same source, and that's all that matters. If it's manipulated from the same source, it's the same equation for all intents and purposes. And I rewrote it, same thing on both. I'm going to cut it short here. This is the same line. Same line means on top and bottom of each other. That is infinite number of solutions. Can I still paste that? Oh yeah, look at that. Infinite number of solutions. We're back. It says solve by substitution. I am solving by logic, practicality, and methods that substitution would employ. Okay? I can't wait to dive out of a oh, great. Maybe you've looked at this problem now and saw what you can do. I'd love to dive out of one of these problems to do a fraction problem with you at some point, but you know, if they don't lend to something like that and there are better strategies at play and I can save time on a video, then let's go and do that. Right here, 3x plus 4y equals 36, 6x plus 8y equals 48. You know what? What I said was kind of very conceited. I am going to do this problem with fractions. If you did look at this big picture, if we divided this by 2, we'd get 3x plus 4y equals 24, and here 3x plus 4y equals 36. One of those no solution cases. So already we know the answer is no solution. If you want to move on, go ahead, that's fine. There are word problems after this. With this one though, I'm going to go ahead and solve with fractions. I hope that's cool with you. Understanding that no variable can get isolated completely by itself without the use of fractions. I'm going to go ahead and get this y by itself, get it in slope-intercept form. I'm going to subtract 3x over. I get 4y equals negative 36, negative 3x plus 36, excuse me. Divide everything by 4, everything. How about I write that step for you? Divide by 4, divide by 4, divide by 4. And I'm going to get y equals negative 3/4 x plus 9. Okay? Negative 3/4 x plus 9. Again, there's a fraction. I mean, you know, there's a fraction. Okay, we have one. I'm going to substitute it in to the bottom equation, in for y. The good news is for this problem, the fraction goes away very fast. We'll get 6x plus 8 times the quantity, negative 3/4 x plus 9 equals 48, okay? And if I distribute the 8, everyone's curious about what 8 times negative 3/4 is. 8 is 8 divided by 1. When you multiply fractions, you multiply straight across. 8 multiplies with negative 3, and I get negative 24. 1 multiplies with 4, and I get 4. Negative 24 divided by 4 is negative 6. This result is negative 6. It's 3/4 of 8. Negative 3/4 of 8. It's negative 6. And, by the way, there's an x. 8 times 9 is 72. Oh, we'll see. That's why I don't like fractions so much, because that is a lot faster. Equals 48. 6x minus 6x. Once again, it's your infamous, the variables are gone, so you're left with a statement to make, and which does not lay claim to any valid truth. 72 does not equal 48. This, of course, is a no solution case. My happy copy-paste guy right here is going to tell you the same thing. No solution for that problem, and we talked about that as you looked at the problem beforehand. Parallel lines. They're parallel lines is what they are. So it looks like we ran into nothing but special cases for the last 6 problems there. I was happy to still provide them for you. I have 2 more problems to do. I believe they're word problems. Let's take a look. Solve each real-world situation by using the substitution method. Okay, now they give you a model, just so you know. You don't have to create the equations here. The number of DVDs sold at a store. DVDs. Blu-ray. Oh, UHD. Let's go for it. Guys, don't stream. The number of DVDs sold at a store in a month was 920, and the number of DVDs... Oh, Blu-ray. Oh, good. The number of DVDs sold decreased by 12 per month. Okay? That looks like it's that model right here. We start with 920, and then the sales sales decrease over time. The number of Blu-ray discs sold in the same store in the same month was 502, and the number of Blu-ray discs sold increased by 26 per month. Let D represent the number of discs sold and T represent time in months. So notice it's not like let D equal DVDs and B equal Blu-rays. We have models representing both of those two things. This is the DVD right here. And this is the Blu-ray disc right here, BD. We have 2 models that represent the number of, D is number of discs. But we're looking for, what do you think the question is? If this trend continues, how many months will the number of DVDs sold equal the number of Blu-ray discs sold? So it's not let B equal number of Blu-rays to equal number of DVDs. They're the same variable. The point is we want to figure out when Blu-ray discs match DVD discs by quantity, when they have the same exact amount. I want to know when we have equal amount of discs after a certain number of months. So right here, I have D equals this and D equals that. This is a perfect scenario for us to use what I called before the equal values method, which says that if a variable equals one thing and a variable equals another thing, those two things equal each other. We're trying to find out when this represents the same exact D, and that's going to approach it at some T, which we can find out. So what I'm going to do is, by substitution, 920 minus 12T kind of takes place of this D right here. And I get 920 minus 12T equals 502 plus 26T. Oh, 50, not 50T. 502 plus 26T. And I'm going to solve for T. And I don't like negative variables, so I'm going to go ahead and add 12T to both sides over here. And I'm going to go ahead and subtract 502 from both sides and move it over there. All right, so plus 12T is gone, minus 502 is gone. I'm left with 920 minus 502. Was that 418? So I have 418 equals 38T. And I don't have a calculator, and I don't know this answer off the top of my head. Oh, yes, I do. It is 11. Divide both sides by 38, and I get T equals 11. That takes 11 months. Now, I'll answer that in a second. First, I'm just going to box the answer. In how many months will the number of DVDs sold equal the number of Blu-rays sold? We just answered that question. We now have to answer the question. Well, I didn't write it yet, but we solved for the variable. Now we have to solve for the variable to represent how many of each is sold in that month. Remember that I've kept saying, and I really should have shown you, I really should have shown you before, and I think now is a perfect time for me to show. I keep saying you can substitute in any equation that you write or manipulate, and that's true. There's nothing wrong with it. You can. T can go in for 11 into the top equation or the bottom equation. Why don't I show you, for the sake of the word problem, that that's actually what happens? If I go to the top equation and I substitute 11 for T, I'm going to get D equals 920 minus 12 times 11. Okay? They sell 920 in some month. They lose 12 disc sales every month, 12 less than the other. 12 times 11 is 132. 920 minus 132 equals 6, 8, 7. I can't do this right now. 788. 788. So that's what D equals when I substitute it in. Let's confirm that when we do the Blu-ray equation that I get the same answer. Remember, the whole point was getting the same D, right? Getting the same answer for both of these things. And let's confirm we got that. 502 plus 26 times 11. Oh, I don't know 26 times 11. Let's see. 286. So 502 plus 286, and that is 788. So we get 788 for that one as well. So D does happen to equal 788, whether I do one or the other. So the point is, you don't have to do it for both. If you want to double check, do it. But you only need to choose one. And there was no easier one this time. Here I had to subtract, but of easier multiplication. Here was harder multiplication, but I got to add. So you choose. All right. Now, do we write this? Now, here's the big thing. This is a word problem. Do we write it as an ordered pair? Do I write 11, 788? Maybe in some contexts, yes. It does make sense that t is the independent variable, kind of like x, and this is kind of like your y, the dependent. But, you know, this has context. We have units. We got to say something. They asked us a question in words. Let's give us the answer again in words. So I'm going to go ahead and type this one out. And I always misspell things when I type here on the video. How many months will the number of DVDs sold equal the number of Blu-rays discs sold? All right. After 11 months, the number of DVDs sold. That tickled my throat. Hang on. Will equal the number of Blu-ray discs. I have to get some water. Sold at 708 a piece. A piece each? I don't know. Sounds good. Why don't you write that down while I get some water here? I'm crying. Okay. I was afraid I was dying there. During a math video, this would never get uploaded. Who will learn about substitution method? Okay. So there's that word problem. Here's the last one, number 15. Oh, I'm past 15 minutes. One smartphone plan costs $30 per month for talk and messaging and $8 per gigabyte of data used each month. That's a lot of stuff. Good thing we have a model. Second smartphone plan costs $60 per month for talk and messaging and $3 per gigabyte of data used each month. Let's see, represent total cost of dollars, and you represent total amount of data used in gigabytes. All right, system of equations here can be used to represent the situation. How many gigabytes would have to be used for the plans to cost the same? What would that cost be? Basically, solve for C and D. And nothing's different from the last problem I did, but I do want to make mention, if you ever have to set up one of these equations, this was a mouthful. This says $30 per month, and that might trick you into thinking that the answer, that when you make an equation, this is going to be a rate. But if you notice here, 30 was used as a constant. The whole point is this is a month cost. What you see as a scenario right here is not about what happens at the end of the year. This is a cost for a single month. So 30 is not going to grow or whatever. 30 is going to be static. It's going to stay the same. It's going to be constant. It's not going to change. The thing that does change is the more data that you use, more gigabytes, whatever, more gigabytes of data used, the more you're going to spend right here. And that's during the month. Within the month, this 8 is going to keep growing based on the number of gigabytes used. Is that, they said number of data? In gigabytes, yeah. So if I use 2 gigabytes of data, it's going to spend $16, things like that. So 30 doesn't change because this is within the month scope. Just want to make sure you know that. Setting up the problem. All right, let's go and solve like last time. Both C's we're assuming to be the same thing, same cost. When do we get the same cost? Let's set both expressions equal to each other. And then let's go ahead and solve for D to begin with. This problem's arguably easier when it comes to the numbers provided, unless it's like a no solution. I'm going to subtract 3D from both sides. I get 5D over here. 3D's gone. I'm going to subtract 30 from both sides. I get 30 over here. 60. This 30 is gone. So I get 5D equals 30. Divide by 5. I get D equals 6. These are two different smartphone plans. But if you plan to use 6 gigabytes of data, it doesn't matter which plan you do. You're going to be spending the same amount of money. How much money will you spend? Well, I do wonder. Let's substitute. I'll use the bottom equation. How about that? C equals 60 plus 3 times 6, which is 60 plus 18, which is $78. So let's write it as a sentence, or to type it as a sentence like last time here. How many gigabytes would have to be used for the plans to cost the same? For the plans to cost the same amount of $78, is it U? Well, how many gigabytes would have to be used? 6 gigabytes of data would have to be used in either plan. So it doesn't matter which plan you use. If you're going to use 6 gigabytes of data, you will be spending the same amount of money. Once you've passed 6 gigabytes of data, if you do 10 gigabytes of data or something, I think this one would cost more. You start by paying less per month, but you pay more for the data after that. So it's one of those things. And I don't know how many gigabytes of data people use. I don't check my stats, and I use the computer more than a phone. But if you're going to use less data, less than 6 gigabytes of data, use the plan that you're going to spend less per month to start with. If you're going to spend more, if you're going to do 10 gigabytes of data, 20, start with the one that's going to cost more to start, because you're going to spend less per gigabyte there. All right, so that ought to do it for the stuff here. That was it for solving systems of equations using substitution. I know it was a lot. What I mean is just, we're done. There were a lot of other strategies. There are a lot of strategies involved and a lot of different situation types. And the word problems gave me something else I could bring up there. So all useful information for you. I hope that the very beginning, especially that number 6, strategically, which variable to choose, is really a nice kind of thing to look at and say, I think it was number 6. Like, I wonder which one would yield the best results for no fractions and stuff. And hopefully I took care of that for you. And hopefully I saved on some costs here too. All right, so that ought to do it for me. Thanks for coming to my virtual classroom. My name is Mr. Robinson, and bye-bye.